I guess that's, yeah, so, well, you've heard the title of my talk now, and this is, by the way, joint work with Benny Siskind. So just so you know, in one slide, everything I'm going to say, Martin's conjecture is some conjecture that's supposed to classify all of the natural functions on the Turing degrees, whatever that means. And our result, well, our main result is that the natural functions, which are also order preserving, which I'll define, are either eventually constant or eventually increasing. So it's sort of a piece of this classification. Okay, but let me actually say what Martin's conjecture is. So arguably the motivation for Martin's conjecture is this observation that on the one hand, it's very easy to build function or Turing degrees in between, say, 0 and 0 jump, or all sorts of other weird degrees. But every time that you run into an undecidable problem in some part of mathematics outside of computability theory, it's pretty much always, well, maybe literally always as hard as the halting problem. So why should that happen if there's all these other degrees? And Martin's conjecture arguably provides an explanation of this. I don't know if I totally buy into that, but for the purposes of this talk, I'll push the propaganda. And the idea basically is to say, well, natural problems should somehow correspond to natural functions on the Turing degrees. So if you can classify those, you can say what the natural degrees are. Okay, so here's kind of the idea. If you have a natural undecidable problem, then you should be able to get a version of that problem relative to any oracle. So that problem should really define a function on the Turing degrees. And that function should be degree invariant. If you start with two oracles that are equivalent, the versions of the problem you get should be equivalent. Okay, if you buy into this, then you should think that undecidable problems give you functions on the Turing degrees. Well, if you don't buy into it, maybe it's still interesting to classify the natural functions on the Turing degrees. So the sort of super informal version of Martin's conjecture is like saying the only natural functions are the iterates of the Turing jump. Which, okay, maybe all I've said so far is why are there no natural intermediate degrees? It's because there's no natural functions, but that's just replacing one kind of vague thing with another. So I think the value of Martin's conjecture really lies in the fact that it gives you a precise mathematical question that you can then try to answer. Whereas this thing about the, where all the intermediate degrees are is still, there's no kind of more precise version that I know of. Okay, so now I'll just kind of get into the actual statement of Martin's conjecture. So if you tried to write down sort of functions on the Turing degrees that you can think of, you'd get things like, well, you can send everything to 0, there's the identity, there's the jump, iterates of the jump. There's these things like the hyperjump, which arguably you can think of as an iterative of the Turing jump, and so on. There's, depending on what kind of large cardinals you're willing to accept, there may be things like sharps and so on. So intuitively on some level, it's just these transfinite iterates of the jump. But obviously it's very easy to build other types of functions. So one example is just for every degree, pick something strictly in between it and its jump. You have to use choice to do that, but it's very easy to do. Another kind of dumb example is, well, pick some degree and everything above that degree sends to its jump, and everything not above that degree send to 0. So that's neither the jump nor 0, it's some kind of mixture of both. And the idea of Martin's conjecture is these are kind of the only types of examples. So if we exclude them, then we'll get a classification that really just does consist of basically iterates of the jump. So to exclude the first type of example, we'll work in a setting without choice. And to exclude the second type, we'll sort of only look at the behavior of functions on large enough degrees. So this second example I gave, when you get to this big enough degree, it's always just the jump. And the idea is that will always happen. Okay, so what exactly do I mean by in the limit? Well, say you have two functions on the Turing degrees. We'll say they're equivalent if there's some large enough z, and above z, they're, well, equal if instead you have functions on the reals, which are Turing invariant. This should say Turing equivalent, but okay, and I'll say that like they're equal on the cone above z. And similarly, you can define an order on functions by saying when you get to a large enough degree, f is always less than g. And I'll say f is below g on the cone above z. Okay, this is really a quasi-order, but if you mod out by the equivalence relation, then it's a partial order as usual. Okay, but more generally, you can say for any set of Turing degrees, if it contains every large enough degree, then it's sort of large, and if it doesn't contain any very large degrees, then it's sort of small. So we'll say it has measure 1 if it contains a cone. There's some z, and above that, you're always in it. And sort of the opposite is if you're eventually never in it, then you're disjoint from a cone. And it's not very hard to prove that this forms a 0-1 valued measure on the Turing degrees called the Martin measure. So when we talk about in limit, we're always really talking with respect to the Martin measure. Okay, for removing the axiom of choice, the usual way that Martin's conjecture is stated actually does something stronger. It takes away choice, but adds this axiom called the axiom of determinacy, which is inconsistent with choice. And okay, if you have just been buying into everything I've said so far, I said, well, we shouldn't be able to construct these pathological functions without choice. Well, what's the justification for adding this new axiom? Well, there's one kind of maybe naive philosophical reason, which is if you just want to rule out that you can build certain types of functions in ZF, then if you can show they don't exist in ZF plus AD, then you're not going to be able to build them in ZF unless you can prove that determinacy is inconsistent, which is hopefully not going to happen. There's also sort of a practical reason, which is the axiom of determinacy is good for establishing structural theorems in descriptive set theory. So it actually gives you some hope that instead of just saying, well, it's consistent that there's no such function, it's actually proving under AD, these are all the functions on the Turing degrees that you can have. And there's sort of maybe another philosophical reason that I think my co-author probably would want me to mention, which is if you interpret natural functions as like functions with some sort of definability constraint, then instead of removing choice, you may just want to say restrict to this, a class of definable functions, like maybe Borel functions or functions in L of R or something. And assuming, well, for Borel, it's a fact in ZF that Borel sets satisfy determinacy, but typically under large enough cardinal hypotheses, any kind of class of definable sets satisfies determinacy. So if we can prove it, if we can prove Martin's conjecture with determinacy, the hope is it just sort of under strong enough assumptions holds for any natural definable class of functions. Okay, so let me say a little bit more about how determinacy actually gets used in this context. The sort of most important fact to know is that under the axiom of determinacy, the Martin measure is actually an ultrafilter. So every set of Turing degrees either contains a cone or is disjoint from a cone. Okay, and another way to say it, which is maybe the most useful way I think to actually use this, is if you have a set which is sort of cofinal in the Turing degrees, like for every degree, it contains a degree above that one, then it must contain a cone, basically just because it can't be disjoint from a cone. So this kind of leads to some sort of pseudo principle or something, which is if you want to use determinacy and computability, the typical strategy is to sort of write down what you want, show it's cofinal, and then determinacy will guarantee it actually holds on a cone. So a lot of proofs are reduced to showing that like above every degree, you can find another degree with some property. So let me give you just a simple example of this. You can prove some version of the jump inversion theorem with this. So there's some large enough degree, and above that degree, everything, the jump can always be inverted. And what's the proof using determinacy? Well, we'll write down the set that we want to contain a cone, which is the set of X for which you can invert the jump. It's kind of trivially cofinal because above every degree, you just take the jump of that degree. The jump of that degree, obviously you can invert the jump because it is a jump. So A actually contains a cone. And that's exactly what the statement of this example is. It's kind of dumb because it's like, you know, an ancient theorem in computability theory that everything in the cone above zero jump, you can invert the jump. So determinacy is getting us maybe a worse theorem with like an overpowered tool, but this is, I think, the basic idea of how it gets used. And the second thing that's useful often when using determinacy in this kind of context is if you have a union of countably many sets, which is cofinal, then at least one of those sets is cofinal in the Turing degrees. That actually doesn't require any determinacy to prove or anything. That's just kind of almost, well, it's not very hard to show if you actually write down what it means. But it's very useful in this determinacy context. So as an example, this is some like maybe the easiest case of Martin's conjecture, let's say. If you have a function which is bounded by a constant a function on the Turing degrees, which is bounded by a constant function, then it's constant on a cone. Okay, the proof is just, okay, if we know that f is bounded by a constant function, it's just saying that for all x, f of x is below c, for some c. Every degree has only countably many things below it. So you can partition the Turing degrees into just these finitely many sets, each one going to a single degree below c. And one of those sets has to be cofinal, and so by determinacy it contains a cone. And on that cone, the image of f is constant. Sorry, did somebody say something? Okay. So let me finally state Martin's conjecture. So as I said, Martin's conjecture will assume the axiom of determinacy. And it says first that every function on the Turing degrees is either on a cone, is constant on a cone, or greater or equal to the identity on a cone. And second, that if you take equivalence classes under this equivalence relation of being equal on a cone, you get a well order, and the successor in the well order is given by the jump. So the successor of a function f is the function which takes x to the jump of f of x. This is maybe slightly different than you sometimes may see Martin's conjecture stated. Usually, for technical reasons, it's stated in terms of Turing invariant functions on Cantor space rather than functions on the Turing degrees directly. Assuming a slightly stronger version of determinacy, those two versions of Martin's conjecture are equivalent. So for the sake of, I don't know, making the talk appear slightly simpler, I'm just stating this version. Okay, and you'll often see the first part of this stated as part 1 of Martin's conjecture, and the second part is part 2 of Martin's conjecture. Okay, so this is, let me mention some relevant past results, definitely not a comprehensive survey. So in the 1980s, Slayman and Steele showed that part 1 of Martin's conjecture holds for functions which are like strictly below the identity. So if f of x is always less than or equal to x, then it holds. So this is saying that if you're always less than or equal to x, then you're either constant on a cone or you're just the identity. Next, let's say that a function is order preserving if, well, probably what you think it means. So if anytime x is less than y, f of x is less than or equal to f of y. So Slayman and Steele also showed that part 2 of Martin's conjecture holds for order preserving functions. Well, they may be proof something slightly stronger than written here, but more or less which are below the hyperjump. If you restate that, just writing out what Martin's conjecture says, the equivalence classes of order preserving functions which are above the identity and below the hyperjump are a well order, and the successor is given by the jump. Okay, and our main result is kind of the complementary result to the one I just mentioned, which is that part 1 of Martin's conjecture holds for order preserving functions. So the previous result was part 2 holds for some large class of order preserving functions. This is part 1 holds for all order preserving functions. So in other words, an order preserving function on the Turing degrees, assuming determinacy, is either constant on a cone or increasing on a cone. And maybe it kind of looks like that's already handled by the first result of Slayman and Steele, which said that you can't have things which are sort of always going down. But maybe the point is this rules out functions which are kind of going off to the side. They're neither below x nor above x. And actually the way we prove this is sort of factors through another result, another case of Martin's conjecture. So define a function on the Turing degrees to be measure preserving if, well, for any x, f eventually gets above x. So I don't know, maybe you could sloganize this like f is going to infinity in the limit or something. I'll maybe mention later why we call this measure preserving. And we show that part 1 of Martin's conjecture holds for measure preserving functions. And now if you look at all the definitions I've said so far, measure preserving is just the same as being above every constant function in the sense of the order I defined earlier. So this is really saying that like functions which eventually get above every constant function also get above the identity. Okay, and before I sort of get into the details of how this works, let me try to give you the picture of what under determinacy, what we know and don't know about functions on the Turing degrees. Okay, so we know that there's all these constant functions. For every degree, there's the function that just always sends you to that degree. And those functions have the exact same structure as the degrees themselves. Okay, there's also obviously the identity, which is above all the constant functions, the jump, which is above that, and so on. Slayman and Steele's first result that I mentioned basically shows that there's nothing which is like strictly below the identity, which is not just a constant function. Our result about measure preserving functions basically says there's nothing that's kind of above all the constant functions, but maybe not below the identity, but also not above it. So there's nothing kind of off to the side over there. An open question is whether there's anything that's just never gets above, not above any constant function. It's like takes you way off to the side, but like never in the limit doesn't compute anything really. So maybe it's sending you only to very generic things or something. So it's unknown whether you could have stuff like that. And it's also unknown if you can have things like, say, strictly in between the identity and the jump, or above the identity but incomparable to the jump, or whatever. By Slayman and Steele's second result, we know they can't be order preserving, but maybe there could be some other weird functions. So this is kind of the picture of current knowledge. So the high-level overview of how we get to our result about order preserving functions is okay, we identified this sort of combinatorial looking condition of being measure preserving, which suffices to prove part one of Martin's conjecture. And then we show that order preserving functions are measure preserving unless they're constant. And the way this works is using a basis theorem for perfect sets, which is kind of an extension of one proved by Groshek and Slayman in the 90s. But I won't really talk about this in this talk. And then we showed that part one of Martin's conjecture holds for measure preserving functions. And that's what I'm actually going to talk about for the rest of the talk, basically. Okay, so yeah, so now I'll, as I said, just be talking basically about part three. So how does the proof for measure preserving functions work? Well, the basic idea of the proof is some sort of basic topological fact about continuous injective functions, and this actually forms the basis of a number of proofs about Martin's conjecture, including some work by Martin and also by Slayman and Steele. Although they don't phrase it as this basic topological fact, but it's exactly the same. So I'll talk about that in a moment, but in our case, to sort of apply this fact, we have to know some more stuff about what you can do with measure preserving functions when you under determinacy. And the basic idea is that we'll use determinacy to show that we always have certain sort of functions associated to a measure preserving function. And basically it's a Scullum function witnessing that the measure preserving function is measure preserving and the inverse of that function. So I'll say this more carefully later. So that's kind of the basic structures. There's going to be this general framework of how you can prove that things are above the identity. And then we have to get it to work in our case by sort of using determinacy to study the structure of measure preserving functions. Okay, so the basic fact is a continuous injective function on a compact Hausdorff space has a continuous inverse. And okay, really what we're interested in though is the sort of computability version, which is a computable injective function on Cantor space is above the identity. So if you, f of x can compute x. It's, okay, basically an application of compactness, not surprisingly, because the basic fact in topology is about compact spaces. Okay, and the import of this is if you want to show a function is above the identity, it's enough to find a computable injective function which is below it. So the whole goal then of the proof is basically to construct this computable injective function below f. Okay, but there's actually, it's not quite that nice. There's some technicality, which is we're not going to get a computable injective function defined on all of Cantor space. We're going to get one that's defined in some sort of nice enough subset. So the actual version of this fact that we'll use is if you have a function defined on a pointed perfect tree, which I'll define in a moment, and it's, okay, if you have a computable injective function defined on a pointed perfect tree, then it can almost compute x, but you need to throw in the tree. And basically, for measure preserving functions, this change is not a big deal because eventually the measure preserving function will get above t. And so having to know t will not be any problem. Okay, so a pointed perfect tree is a perfect tree, so it has no dead ends, and above every node, there's eventually a branching. So that all infinite paths through it compute it. And the basic point of these things is that they're basically, the set of paths through a pointed perfect tree is some kind of representation of all the degrees above the tree. So every turn degree above t has a representative in the set of paths through t. And there's also sort of a version of this determinacy theorem that cofinal sets contain a cone, which is that if you have a subset of Cantor space rather than a subset of Turing degrees, and it's cofinal in the sense that above every x there's some y in the set, then it contains a pointed perfect tree. And so the basic idea is that we can use determinacy not just for subsets of the Turing degrees, but also when we have to work with subsets of Cantor space. Okay, so just to remind you, sort of ultimately we're basically trying to find, we start with this measure preserving function f. We want to find a computable injective function that it computes. And instead there's going to be these technicalities with pointed perfect trees, but that will sort of only come in later. So the basic idea is, okay, we start with this function f. We're going to somehow find a pointed perfect tree and a computable injective function which is below f. We know that by this sort of topological fact that for every x, g of x together with t can compute x. But f eventually gets above t. So f can compute g of x, and it can compute t eventually. So it can also compute x. Okay, but now we need to actually find this g. Okay, so let me just remind you again of the definition of measure preserving functions. Once again, those are functions which, for every degree, they eventually get above that degree. Okay, I've highlighted some part of the definition, which is, this definition is really sort of a for all there exists. And maybe anytime you see that in logic, you should ask what the Skolem functions are like. And so that's going to be the basic idea here. We're going to look at functions that for each x take you to a big enough y, so that once you get above y, f always takes you above x. Okay, and we'll call this a modulus, which I think in some areas is a traditional name for Skolem functions. Okay, so a modulus is just what I said. It's a function that for each x takes you to a big enough degree that above that degree, f is always going above x. And it will be convenient for us, although it's not super important, that the moduli we look at are increasing. So we want that g of x goes above x. If you don't have that, you can always, if you have any modulus at all, you can always get one that's increasing by just taking its join with x. But okay, and it maybe should sound obvious from the definition of measure preserving that every measure preserving function has a modulus. But that's only trivial if you have the axiom of choice. Because otherwise you need some way for each x to, there is some y that's big enough, but you need to actually pick one for each x. And the great fact is that if you assume enough determinacy, this is also true. So determinacy allows you to prove various uniformization theorems. However, there's a technical point, which is that you actually need a stronger form of determinacy than just regular determinacy. Not that I ever said what determinacy was in the first place, but so this proof is actually going to use something slightly stronger than determinacy. Okay, and what's the point of looking at this modulus? Well, once again, we're trying to find a computable injective function which is below f. And it's basically just going to be an inverse. We're going to take a modulus for f, and then we're going to invert it. Basically the same way as in the jump inversion example from the beginning. We'll fix this increasing modulus for f, and then we'll use determinacy somehow to invert it. The technicality is going to be that we can only invert it on a pointed perfect tree. And that's going to be this function that we're looking for. Oh, okay, so suppose that you have this inverse for an increasing modulus for f. the point is that, well, one, it's injective because it's the inverse of some function. Two, it's computable because g was increasing. So if you're the inverse of an increasing function, you should, if g goes up, then if you invert it, you should go down. And finally, the part where we actually use something, the definition of modulus, f can compute this function. So if you start with some x and you apply f, well, remember, g was a modulus. So g is taking h of x to a thing big enough so that f on that is always going to compute h of x. But g of h of x is just x. So x is a thing that's big enough that f computes h of x. Okay, and this is what we were after. So that's sort of why the inverse works. In pictures, kind of what's going on with that last part is we start with this x, and apply this inverse for the modulus. That's taking us down to h of x. Oops. You can go back up with g and you'll just get to the same place you started. Now, if you apply f, once again, I'm just repeating myself, but g is supposed to be taking us to a place high enough that when we apply f, we still can compute the thing we started from. That means this f of x can compute this place we started from, which was h of x. So h is this computable injective function, which is below f. Okay, there might sound something a little fishy about this, depending on how, I don't know, cautious of a person you are, which is, it seems like this should be the sort of thing that's ruled out by Martin's conjecture. So h is decreasing, it's injective, so it's not going to be constant on any cone. So how come it doesn't contradict Martin's conjecture? And in particular, the part of Martin's conjecture that was actually proved by Slayman and Steele. Well, the reason is that h is actually not inducing any kind of function on the Turing degrees. It could start with two things in the same degree and take them to totally different degrees. And Martin's conjecture is only about functions on the Turing degrees. It's not about functions that, there's all sorts of functions that take a single degree and send it all over the place. Like any kind of usual proof of, say, jump inversion would give you that kind of thing. Okay, and it's kind of an interesting point maybe in our proof that we end up studying Turing invariant functions by first relating them to non-Turing invariant functions and then doing stuff with those. And there's maybe actually a point in this where our proof actually in some sense works for measure preserving functions that are not Turing invariant, with the weaker conclusion that they're sort of cofinally above the identity. Right, okay, so now the final part of this is how do we actually invert this modulus? I said it's more or less the same idea as this jump inversion example, but let me go into more detail. So we start with an increasing modulus for f. Since g is increasing, the set of things which are in the range of g is cofinal. Just like in jump inversion, you start with anything, apply g to it, it's above it, it's in the range of g, so the range of g is cofinal. And now we can partition the range of g into sets based on, like, if you start with some y, or I guess, let's say you start with some x in the range of g, you know that the thing that g sent to it, or at least one of the things that g, whatever g sends to it is computable from it because g is increasing. That means it's computable from it by some Turing functional. So we'll just partition the set based on which Turing functional you can use. Okay, and these sets cover the range of g, which we know is cofinal. So this original set of the range of g is covered by these sets. Each one fixes it, is using a single Turing functional. So one of them is cofinal, and so by this determinacy theorem, it contains a point imperfect tree. So, we know for each x in the range of G, there's some Turing functional taking us, sort of inverting G, and we can get a point imperfect tree where that Turing functional is fixed, and that's our H. So this is kind of the end of what I'm really going to say about this proof. Now I kind of want to get into some connections that this suggests. So first, let me say that, as I mentioned, this proof uses more determinacy than just the axiom of determinacy. It uses either ADR or AD+, which are these strengthenings. And the point was basically just we wanted to find this computable injective thing below F. The thing we found was injective because it was the inverse of something. But to find that function, we had to use this uniformization theorem, which isn't provable in just AD. So the natural question to ask if you want to prove this under AD is there another way to find an injective function G like this? And the answer is actually yes for order preserving functions, but I don't know of a way to do it for measure preserving functions. And also even doing it with order preserving functions will still use the fact that they're measure preserving. So that reduction from order preserving to measure preserving hasn't really been eliminated. It's just that this AD proof only works if they're also order preserving. Okay, so I want to mention some of the ideas of this proof because I think it will highlight sort of an interesting connection later. Okay, so we have the same basic strategies before, but we need to find a new way to guarantee this function is injective. And the sort of basic point we'll use is if you have a point imperfect tree and a computable function on it, then you can either sort of thin the tree out so that the function is injective on the subtree, or you can find kind of a full subtree where it's constant, like where you get stuck trying to thin it out. And this is basically the proof of like Spector's construction of a minimal degree or things like that. Okay, so the point is, if you want to get an injective function, it's enough to just make sure the function you get is not eventually constant. So that's really what we'll be working towards. And the idea is we'll ensure that it's not eventually constant by finding some way to associate an ordinal to every degree and making sure that this function doesn't decrease that ordinal. Okay, so I'll call that any function that takes you from Turing degrees to ordinals, ordinal invariants. So the kind of prototypical example is like the Church-Claney ordinal, you send a degree x to the least ordinal with no presentation computable in x. There's some sort of nice things you can prove about ordinal invariants, assuming determinacy. So maybe a nice example, we don't actually use it, but to show you the kind of thing you can do is you can show that ordinal invariants are sort of eventually order preserving. So they can be, I guess, doing wacky stuff down low, but eventually if x is below y, then the ordinal associated to x is less than or equal to the ordinal associated to y. There's a typo where it should just say less than or equal to on the right rather than Turing reducible. And there's the typo again. But the theorem we actually use is that if f is a measure preserving function, then it doesn't decrease these ordinals. So you can kind of think of this as like a weak form of being above the identity in light of the previous fact. So if you have an ordinal invariant, then there's a cone where whatever f is going to has at least an ordinal as what you started with. And once again, there's a typo on the right. You should just say less than or equal to because the ordinal's not Turing degrees. Okay, and let me just mention a little about the proof of this theorem. So suppose this doesn't happen, then by determinacy, there's a cone on which f is making the ordinal strictly decrease. So, either you're greater or equal to on a cone, or you're strictly less than a cone, because every set is either contains a cone or is disjoint from a cone. So, and the main idea is that if f is measure preserving, then so are all the iterates of f. It's okay, maybe not 100% obvious, but not, once again, if you write down the definitions, it's not hard to see. So that means we can find some x large enough so that x and all the iterates of f on x are all above this original cone z. Just take large enough degrees for each iterate of f and then take the Turing join of them or something. So for such an x, we have that alpha x is greater than alpha f of x. It's also greater than alpha f of x, because f of x is on this big cone where f makes you decrease, and so on. But that gives you a descending sequence in the ordinals, so it's not allowed. Okay, and I don't really want to go into the rest of this proof of this alternative proof of part one of Martin's conjecture for order preserving functions, but let me say just the sort of vague outline of it. The key idea is to define some ordinal invariant alpha so that you can find this computable function which is below f and doesn't decrease alpha. And the ordinal is more or less, you can just start with x, take the set you get by closing under Turing joins, Turing reductions, and f. So like everything you can kind of reach from x by applying f. And then take maybe the supremum of omega 1s of all of those reals. Okay, but it's not that important. Okay, so once you found this G that's not decreasing alpha, you can just thin out the tree as in this, Spectre style construction. And you'll never get stuck because sort of, as long as you pick the alpha that's not eventually constant, G can't be constant on a cone because you can just make alpha increase. And G is preserving alpha. Okay, so the fact that measure preserving functions preserve ordinal invariants, well, is just used in finding this G. So G is somehow related to F. Okay, so that's kind of the idea. And I mainly brought this up for sort of what's coming next. So let me back up a little bit though, and try to explain why I was calling these functions measure preserving. So there's some definition or ergodic theory or whatever, maybe it's too fancy of a word, it's just in measure theory, which is the push forward of a measure by a function is just like the measure of a set in the target space is just the measure of its inverse image. And a function is called measure preserving if it pushes forward the measure to itself. Okay, the main reason I bring this up is that actually our definition of measure preserving is actually equivalent to saying that it's measure preserving for the Martin measure in this sense. So a function f on the Turing degrees is measure preserving exactly when it pushes forward the Martin measure to itself. This fact has like a sort of maybe surprising consequence, which is that there's this thing called the Rudin-Kiesel order on ultrafilters on a space, which is defined in terms of push forwards of measures. And if you know that measure preserving means measure preserving in the sort of measure theory sense, then our proof of part one of Martin's conjecture for measure preserving functions is actually showing that the full part one of Martin's conjecture for all functions is equivalent to some statement about the Rudin-Kiesel order. Specifically, okay, if you maybe know what the Rudin-Kiesel order is already, specifically some statement saying that in the rooting Kiesel order of ultrafilters on the Turing degrees, the Martin measure is minimal, and there's no other ultrafilter equivalent to it. So that's the first fact. But there's it seems maybe there's something going on here. And so if we keep looking at the ultrafilter, well, anytime you have an ultrafilter, you can try to take ultrapowers of things. The Martin measure is countably complete. That's basically just because you can take joins of countably many Turing degrees. So the ultrapower by the ordinals is well-founded. So anytime you take an ultrapower by a countably complete ultrafilter, you get something well-founded. And the thing I was calling an ordinal invariant before is really just a representative of this ultrapower. It's just a function from the Turing degrees to the ordinals. And the definition of measure preserving function means that it induces an embedding on this ultrapower. But embeddings on well-ordered sets are always non-decreasing. And if you unroll all the definitions, this is actually just giving a proof of this theorem I mentioned before, that measure preserving functions don't decrease ordinal invariance. I guess sort of what seems to be going on here is that there seems to be some connection between these results and things about the ultrafilter, the Martin measure as an ultrafilter and the ultrapower by it. And it turns out that ultrapowers by the Martin measure have been studied in descriptive set theory in the context of the descriptive set theory of L of R. There's also something in that context called a generic ultrapower, which is defined using a notion of forcing where the conditions are point and perfect trees, which also seems to have some similarity with some of the proofs of things about Martin's conjecture. So I don't know if it will pan out, but it would be really, I think, wonderful if this meant that we could study the structure of functions on Turing degrees and study aspects of Martin's conjecture by using these tools from descriptive set theory. And it would be especially great if proofs could become clearer when working either in the ultrapower or this generic ultrapower. And I gave one example of this proof that I think in some ways becomes arguably simpler in the ultrapower. And it would be nice if that happened in more cases. So I guess that's more or less where I plan to end on. So this is the end of my talk.
Thank you. Very nice talk. We'll have a round of applause quietly, I guess. We'll open the floor up for questions. Please unmute yourself and ask your question. So I'll ask a question. So you have the one example, which I think was jump inversion, right? Do you have other ones? Another example at all?
Of what? Of using?
Where you use, yeah, that you wanted to use this ultrapower, to study the Turing degrees by using but you talk about at the very end.
Yeah, the main example is this thing about this theorem about measure preserving functions and functions from the Turing degrees to the ordinals, where the proof is basically just saying that the Martin measure is countably complete, so the Martin ultrapower of the ordinals is well-founded. There's some other examples that you can kind of reinterpret things as saying something about the ultrapower, but it's maybe not, it doesn't really seem to change anything or give you any new perspective. I think there may be more examples, but yeah, I don't have any great examples besides that currently.
What's the one that you think of that's close? It doesn't give you any new insight. I'm just curious.
Well, okay, some of the proofs that I gave earlier about, say, just proving that part one of Martin's conjecture for measure preserving functions, you can sort of rewrite things in the ultrapower, but it didn't seem to make things easier. But I'm not sure if I have the right framing. So there may be a better way to do it.
Okay. Thanks.
Can I make a comment on that? On another example? One way that determinacy was used long ago was to prove the existence of an upper cone of minimal covers, where B is a minimal cover of A. If A is less than B, then there's nothing in between. You can easily show that the minimal covers are cofinal just by relativizing the construction of a minimal degree, and that gives you an upper cone of minimal covers if you assume AD. And in fact, I proved the existence of an upper cone of minimal covers long ago, before AD was proved, say, for Borel sets, by using just enough of AD that had been proved and a slight trick to get that. And then came the question of can you get some information on what the base of such a cone of minimal covers might be. And so Richard Shore and I showed that 0 to the omega is the base of a cone of minimal covers. And I think it's still not known if there's any degree strictly below 0 to the omega, which is the base of a cone of minimal covers. Now, a little bit off the subject, but brought back some memories.
Thanks, Carl. Other questions or comments, please?
Oh, I have another, if I may.
Sure, Carl.
The countable completeness of Martin measure, that's pretty clear from the axiom of choice, but how do you get that without the axiom of choice?
Yeah, I should have mentioned maybe that I guess typically most things about Martin's conjecture are stated assuming AD plus like maybe dependent choice for sets of reals. And but actually, I guess determinacy implies already enough choice to prove it. So determinacy implies countable choice for sets of reals.
Okay,
that's all you need.
There was another question somewhere.
Yeah, here.
Okay.
You have been quite reluctant at the start to actually make the claim that sort of the existence of natural intermediate problems would give you some function like that. Is that just because you didn't want to have that discussion, or do you have some reasons to not always concur with that statement?
I don't necessarily have any strong reason to disagree with it, but I think that it's just not clear to me that every problem obviously admits a sort of canonical relativizable version. I mean, there's, say you take, the problem of you're given a polynomial with integer coefficients and you want to know if it has integer roots. It's not, I don't think there's like a totally obviously correct way to relativize that problem. And I think there's reasonable things you could do, and they do end up being equivalent to the jump, but it's not clear to me if there's like an obviously correct way to do that.
I mean, there would be the potential candidate in the very same question, just ask for just asking for solutions which are rational numbers.
Well, I mean, relativizing that problem to an arbitrary Turing degree, it's like, I think there are ways to do that that always yield the jump, but it's not, to me, it's not clear like if there's like a canonical way to relativize that problem.
I'll just comment in that case, there is one like nice way that Russell and some of his co-authors have done it that yields something that's not degree invariant. So that's the other thing that can happen.
I muted myself, I'm sorry. Are there more questions? If not, we'll thank Patrick once again for a great talk. I'm gonna stop the recording, and generally we just hang around for a while and talk.